Okie dokie. Welcome to the CAB302 lecture on software patterns and refactoring. So I've transitioned from using a low quality headset microphone to using a low quality lapel microphone, so I don't know if this will make the quality better or worse, but hopefully there should at least be less microphone scratching, because I did go and watch some of my mini lectures and I found that it was really distracting. But anyway, we'll just get right into it. So, this week what we're aiming to do is to understand that software development need not be from scratch, and that there's a body of experience of good ideas and good solutions to be exploited in any problem. Basically, it's all about making use of or reusing existing software development solutions to certain problems. So it's not so much code reuse, it's not where we're making use of a library or copy-pasting code from somewhere. It's just that we are taking a sort of template of a solution to a problem and applying it within our own software where it applies. So we're aiming to learn about some of the more important of these patterns and how to use them in practice. And to understand that ugly, inelegant, that's the design pattern part. In the refactoring part, we aim to understand that ugly, inelegant code can be improved systematically without introducing defects. This is a very important concept in software engineering, and it's especially important when we're making use of things like test-driven development. From the sort of red-green refactor, we can see that test-driven development is a strong user of refactoring. And we're aiming to learn about the most important refactoring techniques and how to apply them, with and without tool support. So refactoring isn't something you'd necessarily need an IDE to accomplish, but it becomes a lot easier with tool support. So, what is a software pattern? Well, just a bit of background. It's the whole idea of invention being good. We do need to invent solutions to things occasionally, but reinventing a solution is not necessarily quite as good. And as developers, we frequently tend to reinvent solutions to problems that have been solved many times before. So if you come up with a way of doing something, and if it's a good way of doing something, there's actually a pretty good chance it's actually been discovered before. Not always, though. And sometimes our new solutions are exceptionally good, but most of the time they're a bit substandard. They're not necessarily going to be quite as perfect as something that's been done by others before. So in the real world, we often see products only after they've been developed and refined. We don't see the failed prototypes, of which there are many, and some of those can fail rather spectacularly. So we tend to only see the things that have sort of gone through the process of applying and testing things out over and over again, not the sort of first attempts. So, and a good example of that is the earliest light bulb. And the idea was that during development, Edison used 1,000 different materials or combinations of materials for the filament of the light bulb. And this was a very important part of it. Some of those just vaporized, most of which vaporized instantly, and therefore weren't all that great as light filament. But with software development, we usually keep the first approach we come up with. We come up with a particular solution for something and we just apply it and we move on, as long as it actually works. It's not necessarily the best way of going about solving a particular problem. So this led to something called the design pattern or software pattern. The terms are pretty much interchangeable. A lot of people will refer to them as design patterns after the book, the so-called Gang of Four book, Design Patterns, Elements of Reusable Object-Oriented Software. It's called the Gang of Four book because there were 4 authors behind this book. That's just a thing that people like to do. And we're just going to be introducing design patterns, talking about some of the ones that most cover, that are most applicable to our kind of work. We're not covering everything. And there's more about this sort of thing, about sort of looking at how we approach problems from a software engineering perspective in CAB302 programming paradigms, taught by Wayne Kelly. But this lecture is just a taste. And the basic idea behind... I should also point out that design patterns don't necessarily mean that you have to get this book. This is a pretty good book. It's available in the QUT library if you're able to get there. But all of this stuff is available online. You just Google design patterns and you'll find, no doubt, tons of information about these patterns. They're very well known, very well documented, and so forth. So the basic idea is that they are reusable solutions to common problems. They're a general template applicable to many different situations. They're not a complex domain-specific design. They're limited in scope. So the idea is that they aren't for, working within a particular industry or anything like that. They are just for writing software. They tend to be a little bit limited in terms of they're designed to help you address certain software engineering problems that come up in object-oriented languages. And they're after a particular style of object-oriented programming, which is the style that we use in Java, but it's the style that also came from a style that people used with C++. And that's what I think the majority of the code in the Software Patterns book is actually demonstrated in. It's using C++. So these are more problems that are they're not specific to a particular programming language, but how important they are does depend on your programming language, and specifically the paradigm used. If you're writing, a procedural code without classes and things like that, you probably won't have a lot of use for much of the stuff in software patterns. Same thing if you're using a functional programming language. So it's mostly designed to work within the bounds of these kinds of object-oriented programming languages. And the software patterns capture your design intent, but not the full detail. They aren't something you can just directly translate into code for the most part. Some of them, like Observer, can actually be turned into a library. You can have an Observer library where you have typically an Observer class and an observable implementation or abstract class. But for the most part, these are things where you have to actually read about the design pattern and then translate that implementation into your specific application to meet your specific needs. And so most of them aren't reusable classes, and they're not specific implementations. Design patterns aren't code. They're patterns that you can use to write code. And they're not algorithms either. So algorithms are meant to solve computational issues rather than design issues. So, for example, you might have a shortest path algorithm. Now, it's probably pretty logical to go and find an existing shortest path algorithm rather than try to invent your own, because there's a lot of good ones and a lot of the design problems that come with them have already been worked out. Same with things like line drawing algorithms, things like that. But given that we aren't, but these aren't the kinds of things that we're covering in software patterns. Software patterns are about the design of your application. They're about which classes you need in order to solve a particular problem, how those classes call each other's methods, how you use abstract classes, how all this stuff is linked together, that sort of thing. That is what a software pattern is designed to address. Software patterns in object-oriented programming show relationships between conceptual classes and methods, not necessarily your actual classes and methods. What the actual classes you have will depend on your specific implementation and what specific domain problems you have to solve. And so when these are covered in the book, they don't show actual classes or methods or anything like that. So the idea, as they're described in the book, is that they are descriptions of communicating objects and classes that are customized to solve a general and oft occurring design problem in a particular context. And another advantage is that this book helps to establish a common language. The idea is that, the analogy there is to engineering handbooks. They're designed to collect the wisdom of the profession and standardize those standard designs. And so the book provides a taxonomy and catalogue of these certain designs, which is quite powerful because it provides a common language for describing solutions. So rather than needing to actually go and describe exactly what you're doing, you might say, all right, I've got a class here, and this class has, references to these objects in it, and these objects are all implementing this one abstract class. Rather than needing to describe it in order to get across what you're trying to do, you can just use the language from the Gang of Four book, and people who are in the same profession as you and who have also looked at design patterns will know what you are talking about. And if not, they can go and look it up. So it enables a common language to describe these types of design choices. Each pattern name denotes the class relationships and a defined set of interactions, but once again, it's not a matter of providing you with library code. So the Gang of Four book breaks up the design patterns into 3 catalogues, covering the creational, structural, and behavioral design patterns. And there's a list with a brief description at the end of this lecture, but otherwise you can mostly just Google any of these and you'll find plenty of information about them. We're going to be looking at 3 particular patterns in this lecture today. The factory method, which is basically creating a common interface to let you create multiple similar objects that are of different classes. So this is a way of getting around, I guess, some of the limitations of the constructor, in that a constructor can only construct, the object that the class that it is implemented in. So if you have a particular class, the constructor needs to always construct that particular class. We'll see why it can be useful to have a way around that. Next is the singleton, which is this idea of a class where there's only one instance and you need to have a global point of access to it. So sometimes disparagingly called the global variable. The idea with the singleton is that there are some things where you need your entire application to be able to access this particular instance of something. Potentially because it's very expensive to create, or because it has some kind of lock on a resource. For example, if you have a database, it's probably best to only have one object actually communicating with that database, rather than having potentially multiple objects then getting on each other's toes. Or, in the case of a file, especially if you've got it open for writing, you can only have one handle on that file at a time. So if it's something shared, like a log file where all of the error messages that are generated throughout your application need to go, you'll want to have just one instance of it, and you'll want to be able to access that instance from anywhere. So the singleton is a design pattern to let you do that. Finally, there is observer, which is probably the design pattern that you've used most often, even if you don't know it yet. And it is to establish these one-to-many dependencies between objects. And so when one of these objects, when one object changes its state, all of its dependents are notified and updated automatically. We'll see why this is a powerful design pattern fairly shortly. But for now, let's just go to the factory method. It's a fairly simple approach. There is another similar design pattern called abstract factory, which you might occasionally hear of. That is a bit different, but it also ends up involving factory methods. So the idea is that a factory method allows creation of objects without exposing the creation logic. And that's a good example of encapsulation. So the limitation behind a constructor, as we mentioned before, is that a constructor can only construct one particular thing. So let's say I go and create my class. Now, and my class has a constructor. This constructor can only be used to construct an object of type myClass. Whereas if I have another method, that method could end up constructing any object I like. And a lot of the time, so let's say I create another one. Let's go and make like my other class. Once again, its constructor can only be used to create this one thing. But if we have a factory method, so let's create let's say public static object, so that we can create both factory method, and we'll just for now we'll just use a boolean to determine whether we get the other class or not. If other will return new my other class, else return new my class. And this way we can go and call this method, and based on the parameter passed to it, we will get a particular object created. And we would essentially use this in our code instead of using the constructor methods. And this is a fairly powerful construct. One of the reasons for which is, when you actually call a constructor, if you say, my class equals new my class m equals new my class, then this is essentially fixed in terms of compile time. So if you fix that compile time, so let's say you wanted to get some feedback. For example, you want to see if if args.length is greater than 1 and args0 dot equals other, to see if you could greater than or equal. Okay. In order to generate the other class, we can potentially call a different constructor at this point, but that doesn't really help us, and we certainly can't use multiple instances of that all that well. So the idea is that we encapsulate this kind of logic into a factory method, and that will decide what class we get out of it. These are best used in conjunction with interfaces or abstract classes, in that we can define a common subset of their functionality. So we might say create an interface, my interface, and just have these two inherit from it. And this way, these two classes can implement, the shared behavior that is defined in my interface, and we can just return one of these instead. So that rather than just having the stuff that we get, that object gives us, we can actually call factory method, pass in some particular result, and we'll get back a my interface, and then we can go and call whatever we want on it. For example, we could just say, just have a method void hi, and go and implement that in here and here. and maybe have them do something different within each class. So that's the basic idea. A factory method is very easy to go and create. There's also some other small advantages you can get from making use of a factory method. The other thing is that if you use a constructor, you're obligated to actually, create a new instance of that class. But within certain types, it may actually make more sense to grab an existing implementation of that class and return it instead. So you're not really constructing something at that point, but it might actually be, a better way of going about it for your particular problem. You gain a lot more control if you have everything going through this factory method, because of course the whole issue with, what happens when you update your software later. If you're using constructors, then you're pretty much tied into using that constructor. But if you make use of this factory method, you gain a lot of flexibility. You can return different classes, you can return a subclass of the class instead of the actual class. You gain a lot of flexibility by using a factory method that you don't have in a constructor. So this could be, for example, using different file types or changing from one database to another. Although, as we've already seen, you can already change from one database to another in quite a flexible way using by using JDBC. But in essence, the JDBC sort of provides some of this because we're using the driver manager to construct a connection object, and we'll get a different connection object based on the type of database. So really, the JDBC driver manager approach is an example of an abstract factory. The factory method is particularly useful for object-oriented languages, but it's more general than just object-oriented. It can be used in imperative languages and the like instead. It's sort of a very general approach where we just abstract the creation of many similar types of things into one particular source, so that we can choose that based on different things. So often an example I give for a case in which you might use a factory method is for file access. So let's say that your program wants to be able to access plain text files, but also compressed files that are, say, compressed with gzip compression or something like that. And so you don't want to go and write a whole bunch of common code that needs to either support compression or not support compression. So you don't want to have to write different code for, say, reading in your billboard format. You don't want to have to write separate code in these different classes in order to handle compressed and uncompressed files. So instead, you might have something like a file class. You might have, say, an interface called file interface, and then you might have class plain, or let's call this uncompressed file, which implements file interface and, say, compressed file. And then you can just have this with the standard set of operations for a file class. You probably wouldn't implement this from scratch because Java already has the types you need for doing this. But if we were, we would probably have, say, some kind of, open file method, and this would be the factory method. So that open file method would take a path to a file and would return a new file interface. But it would actually look at, say, the extension of that path, or maybe it would look at the contents of the file to determine, do we want to create a new uncompressed file, or do we want to create a new compressed file, whichever we go with. And so we can then, the file interface itself might have things like, I don't know, it might have read byte, void write byte, and probably a close method as well. And so we would just have different methods for these within uncompressed file and compressed file. The uncompressed file would just read and write as is normal. The compressed file would make it go through this compression scheme. But either way, once we've created this and we've got this factory method, we can just write our normal code to go and say open, file interface equals open file, and we might get something from the user. We might just take, the first argument, something like that, from the command line, or we might get something that's from a JFile chooser or something like that, and then we can just do, read bytes from it, write bytes to it, whatever, without needing to know about the different types of compressed files. And later on, let's say we decide to add more file formats for it. Let's say we later on want to support bzip2 files. We could then create another one of these and implement bzip2 compression, and then we don't need to go and change anything in our code that actually makes use of the file code. So this is a very flexible way, compared to if we had some kind of special code where we check if user input dot contains dot bzip2, and then we went and bz2 file was new. But then all of a sudden we have to go and change all of this stuff if we go and update it and change the way we do some of this. Instead, we encapsulate that within the factory method and everything is good. So this is just a very basic toy example of using a factory method to create a particular instance of an enumerated type. So a coin that says heads or tails based on the input. There will normally be some kind of parameter passed to a factory method to specify what kind of object you want. But the idea is that by having this choice made in a factory method, you can have this happen, for example, at runtime rather than just at compile time, which is what you're limited to if you use a constructor instead. Another example of this with two different animals implementing the pet interface, and with different implementations of speak, we could then create a pet factory that creates a new pet based on the type that we end up passing it. And that's all fairly straightforward. Okay, so that's all for factory. The factory method is very simple. As you can see, it's only lines of code to really do work with it, but it's at the same time a very powerful construct. And this idea of you create a particular method and then call stuff within it, and then pass an argument to it to get it to produce a particular result, is a design pattern. It's sort of something that's come up enough times that the best solution for this has been worked out, and that solution is the factory method. You'll actually see these used quite a bit within Java itself. There are numerous factories within the Java development kit, and you'll find that there's factories that produce factories and things like that as well. So they make quite heavy use of design patterns. Next is the singleton. So the basic idea of a singleton is that you use this pattern when you just want one instance of an object. So this might be things like your window managers, print spoolers. So you might have many printers and you might have many applications or many forms that target a printer, but you probably only have one print spooler. Say if you have a handle on a particular file system, or in the example I gave before, a logging system. Like you have all of these different parts of your application that need to produce log output. but you only want one log file, and you might make the access to that log file a singleton. What the singleton design pattern gives you is the ability to ensure that only one instance of a class gets created. It provides a global point of access to that particular object and allows future clients to access the instance without affecting previous clients. So this is another advantage of removing the constructor, essentially, and requiring people to use this particular method in order to gain an instance of an object. The idea is that you're able to basically funnel all of the accesses to this object through this method, and then if you've got this single point of access, you can change things as you want, and you're able to future-proof your design. So this is just a bit of an example of the code in order to create a particular singleton. And this particular way of doing it is making use of a private inner class, in this case called singleton holder. And what that does is that it actually holds access to the instance of singleton. This way it protects other code from being able to access it. And so this is sort of a bit of a paranoid way of making sure that other stuff can't make use of it. In many instances, just a private variable would probably do, but nonetheless it is a popular approach. And the idea there is that it will then be constructed when this class is instantiated, not instantiated, when basically at the start of your program, this instance will be constructed. So it will create an instance of this singleton and store it here as a field of this inner class. And then you then have a getInstance method which will return that. This ensures that instance is only created once, its constructor is only called once, and that every class that wants to make use of this has to go through this getInstance method. So in this particular example here, these two lines will both retrieve the same instance of that singleton. They will get the exact same object back, and so if that object is, say, mutatable, they are affecting one of them will also affect the other. So there's a few different instances where this kind of thing might are useful. I'm not sure if this is the right slide, but I'll just give a bit of an example of how we might use something like that. So if we go and I might just go and copy paste that code. Hopefully it doesn't get broken up too much by this. If we go and create our singleton here, okay, very nice. And so the use of the static class here basically protects that singleton instance from being accessed by anything else. And it even, potentially provides some small amount of protection against finding it via reflection, although I'm sure you can still end up getting the class, managing to get to that instance if you really want to. But the idea is that we, the other part to this is that the constructor is protected. That way other code can't go and make use of it. So our, if we're going to do that, I better put this in a package. Week 10, move singleton into that. In fact, move all of it into that. There we go. Okay, so in our main method, for example, if we singleton s equals new singleton, it is actually fine with it. Oh, it's fine with it because we're in the same package. We might want to actually make the constructor private. Yep. Okay. So we've made the constructor private now. What protected does is that it still allows access within the same... Wait a minute. Protected shouldn't actually allow access to that. I'm not sure what's going on. We'll make it private anyway, just to keep this safe. So, instead, if we want to gain access to singleton, we need to call singleton.getInstance. And we'll actually see quite a few examples of this when we're doing GUI programming. There's, in Swing, for example, there's the look and feel get. There's a manager for this that we can actually get. That's just sort of one example of it. But that's the kind of thing. It's where we have one instance, and it's a bad idea if there are multiple instances, but we want to be able to access it from everywhere. Now, this does have some, and of course we can just go and then add stuff to this singleton class as we require now. So we could have it private, do something, make that void, and yeah, so we can get that instance, and we can then call, why don't I make it private? And then we can call various methods on it and things like that. The one thing we can't do is create a copy of that particular class. So that's, yeah, we can't create another singleton. Only the code that's within singleton can do that because we've made the constructor private. Ooh. Okay. So that's the basic idea there. The third design pattern is the observer pattern. So the basic idea behind the observer pattern is that the common problem there is in synchronizing state and or responses from across a collection of objects in response to an event. So when there are changes in the subject, so we have something that is to be observed, so that's the subject, or sometimes it's called the observable. And so when something happens to the subject, the observers are notified. And the reason why this pattern is powerful is because it helps to reduce something called coupling, which is, commonly viewed as being undesirable within an object-oriented program. So the idea with coupling is that it refers to which pieces of code depend on other pieces of code. So if a method instantiates a class and calls a method on it, then that class is considered to be pretty tightly coupled to that particular method. So if that class changes or something like that, that method may need to be updated. The idea with the observer pattern is that it's a way of keeping the subject from knowing about its observers and keeping the observers from being too dependent on the subject. So it sort of keeps them at arm's length and has some sort of mediation happening between the two. It's also known as a broadcast or subscription model, and we've used this quite a bit within our GUI programming. And one example of the observer design pattern in GUI programming, let's just go and create new okay, so let's say we create a nice new JFrame, and we go and frame, get content pane dot add button. In order to do that, we'll need a button equals new JButton on a button, and then we just go and unpack it, make it visible, and then run it, and we'll have a button. We'll have a form with a button on it, hopefully. So the way we actually wire up a GUI to do something when you click the button is with this add an action listener, or any other type of listener. There's a few different listener types that are appropriate here, and we can then just go and create our new action listener and go and write some code to do something when that button is clicked. And that's all fairly straightforward. I see, it was, yeah, the window was still open because I didn't set up a default close operation. But there we go. So what you can interpret here is that listener actually means observer. This is using the observer model. And the idea is that the button doesn't actually know about about the individual classes that may be observing it, and it doesn't go and have explicit code that it goes and runs when it gets clicked. Instead, the way you wire up a GUI is that you create your button, and then if you want to assign it functionality, you go and you say, this other class knows to do something when a particular thing happens. And so the class that you've created that goes and reacts when a button is clicked, it doesn't actually know about the button. All it gets is an action event, so it is actually loosely coupled to the button. It doesn't even know about the button. On the other hand, the button is loosely coupled to its observers as well, because it's the only requirement based on its observers is that they implement this action listener interface, and all button has to do is just loop through everything that's been added to it, every observer that's been added, and call the action performed method on all of them when that button gets clicked. And so the button doesn't know about your code either. What this does is that in a normal case you might have a one-way coupling relationship between the button and the code that executes when you click it. But through use of the observer design pattern, that coupling has been eliminated basically. And so you can, and I mean, there's different types of listeners, which is another pretty common paradigm. You can have different types of observers for different kinds of things happening to this particular subject, this button. For example, you don't want to necessarily just do something when the button is clicked. You might want to do something when the mouse is moved over the button, or when that button receives focus, or when a key is pressed when that button has focus, or anything like that. So there's all these different potential options of things that an observer might want to know about, and those are all handled through this process. So that's what I meant when I said that you've probably been using this design pattern already. It's just that you've been using it without necessarily knowing it. So one example scenario is with a weather monitoring system, where you have a weather sensor which notes change in temperature, and then you have various observers that want to do certain things. So one of them might be a client GUI that displays the temperature. Another one might be a weather modeling system that takes that temperature change into it. So if you're running a meteorological center, then you might make use of a whole heap of different sensors that are passing data to go into a big neural network or whatever that you use to predict the weather. So these might be your sort of example. You've got the sensor, and then you've got these different observers that take that sensor's results. And the sensor might just be a plain temperature sensor, so it just sends that to these observers when the temperature changes. and that those observers can then react to that information in different ways, just in the same way that you may have multiple pieces of code that are action listeners for a particular button, and those pieces of code may do different things when that button is clicked. So how does it work? Well, somehow we work with these subject and observer classes and specify the relationship between them. The idea is that a subject has one or more observers. The subject will notify the observers when things change. In response, observers will update. So the update could be a query of the subject state. So often the information might not actually be in the update, because of course you can query the sensor object to get its temperature. Instead, you just send the update to remind the sensor, this thing exists and it has recorded some kind of change. You'll need to then query it to get that change. Or the update might actually contain that information in it, which might be useful if you've only got one thing that it's sensing, because if this is a temperature sensor and it can only return the temperature, then you know that if this goes and makes a request to the sensor, it will be trying to get the temperature from it. So you might just send the temperature in that update to save a bit of communication. And of course, this is the magic behind GUI events and responses. So in GUI libraries, is usually done via an interface. So our observer has we have different observer interfaces based on the kinds of observations that are being made. And this is the typical structure. The main way is that we typically have methods for attaching and detaching an observer. And this is sort of a crucial part in it. So we often have third-party code that actually does the connection. So if we consider this example here, we actually have three classes in work here. One is the J button. The other is this anonymous inner class here that is just that is the observer. And the third is this code here, which actually goes and ties those together. So the button doesn't need to know about this listener. The listener doesn't need to know about the button. It's just that this third-party code goes and ties them together. And that is also a crucial component of model view controller type setups. And so this is how that sort of works on a bit of a time lapse. So what we have there is the vertical axis is time, and so we've got this subject and then a couple of observer classes. What the subject does, what happens is that at the start here, those two observers get attached to that subject. So that's usually stored in the form of some kind of list type. So you might just have an array list of observers, something like that. In fact, I think if we go to this add action listener code, we can actually go to that implementation, have a look at the Java source code. So what happens is that we've got this abstract button class here, and it maintains a listener list. And what is listener list? Whoopsie. It is, okay, it's an event listener list type, and we can add things to it. Or we can remove things to it, because the option is also there for removing an action listener. Finally, we've also got a method used in here to actually retrieve the action listeners, and that might be used when something actually happens. So when that button is clicked, it will then iterate through all of the listeners in this listener list and update them all. So yeah, those two observers get attached to that subject, and when that subject state changes for some reason, it will then go and update the observers. So it will just loop through. So normally you'll have a method called something like notify observers, and that will loop through all of the attached listeners and update them. And those listeners might, in response to that, go and retrieve the state of a concrete subject in order to see, for example, what the current temperature is, and then go and do whatever processing they need to do. So we'll just loop through those two listeners updating them both, and then return to normal processing. And so in terms of what the code ends up looking like, we typically have subject having some kind of, we might have subject having some kind of interface here, where we have the typical common methods that are associated with a subject observer. But we definitely have observer as being an interface, and the only thing the observer interface needs is an update method, and that's basically the same as that action performed method we have here. You want this to be as lightweight as possible, with as little stuff to incorporate as possible, so that it's very easy for someone to go and create observers, because making them, and of course one method, if your interface only consists of one method, that's also an advantage because it means that you can make use of the lambda to make your code look even neater. And so there's an example of some code that actually uses it. So this one being, for example, a temperature sensor that implements this particular subject. And what it does is that it keeps a list of observers, in this case stored as an array list, and it then goes and has its own custom code for setting the state of that particular observer. And what happens is that, and as well as code for actually attaching and removing the observers, and this notify observers method, which will then be called when the state gets changed. And it will then iterate through all of the list iterators. We could probably use a proper for each loop for this rather than making use of the iterator, but that's a way of doing it. Finally, there's temperature monitor, which is an observer of temperature sensor, and as we can see, it just has its own code for handling this. So, for example, it might get the state of that particular subject when it gets updated and just store that in this observed temperature variable. And then it can go and do whatever other things it needs in order to produce a report or something like that. And finally, you have the main method that then goes and ties those together. So the main method is the only piece of code that actually needs to know about both the concrete observers and the concrete subjects. So it knows about the temperature sensor and about the temperature monitors, and it is able to go and tie all of those together without them needing to know about each other. So you've created, a very reusable construct there. You can then go and create different types of subjects and different types of monitors and tie them together in whatever way is convenient without the individual pieces of code here, without the temperature sensor or the temperature monitors needing to be modified. And that will then produce some output. The idea is that as this temperature sensor is modified, often you would actually have the notify observers called within that set state method itself, but this is just how this example shows that it's being done. So what are the benefits of that? Well, you get very loose coupling between the subject and the observers, but tight coupling between the observer and the subject itself. So the observers do need to know, the observer needs to know that this is a temperature sensor, because, obviously it needs to do different things based on what kind of sensor it is. But the sensor doesn't need to know about the observers, it just needs to know some object out there is interested in finding out when this sensor gets new information. So we just need to tell all of those objects, and they'll sort of ask in advance if to be subscribed, to be notified if there's any updates on the temperature via this attach observer method. New observers can be added without changing the subject, so because the subject doesn't know, we can just go and create a new observer that goes and produces, say, a graphical plot of the temperature, or something like that. And of course, objects which change the state of the subject may be completely unaware of the observer collection, and that because that may be a far greater impact than the local change. So in summary, software patents are a terrific boost to the reliability of software and to the efficiency of its construction, because if you become familiar enough with these patterns to recognize when a particular situation calls for them, you don't need to go and work out your own solution to it and potentially re-engineer the solution if your initial attempt doesn't work. You can just decide, oh, that's a case where I need an adapter, or that's a case where I need a flyweight, and you can just then go and implement that rather than needing to sort of do too much original design. Software patents preserve the wisdom of the community and help us to find good solutions to standard problems, but they don't provide us with libraries, so we need to adapt them to fit our specific needs, and that's why this sort of approach with interfaces is very important. They allow us to determine a sort of specification that things need to follow in advance, and then we can go and create things that fit that specification and then use them. Just as importantly, patents give us something to fall back on when we're not sure what we need in a particular case, because when people are sort of under pressure to get stuff done, they tend to take shortcuts and not be thinking as clearly. But by following patterns, we produce a more stable solution in a similar time frame, because you're not needing to invent a new solution, you're just using an existing one. And as a result, you also make far fewer code errors. Okay, and that is it for software patents. Next, we're going to have a look at refactoring. Refactoring is essentially the equivalent of software patents, but for our actual coding. So software patents or design patents apply to the design of our applications. That's when we're working out what classes we need and how those classes work together. Refactoring is a similar sort of thing, but it applies more to the actual physical code of our application, the lines of text that we write and then shove into a compiler to generate working code. So the sort of quote here from Robert C. Martin, duplicate code is the root of all evil in software design. When a system is littered with many snippets of identical or near-identical code, it is indicative of sloppiness, carelessness, and sheer unprofessionalism. It is the gilt-edged responsibility of all software developers to root out and eliminate duplication whenever they find it. Duplication, it's very easy to see how it arises, and it's because in a lot of cases it can just be easier to copy-paste an existing working piece of code and then change it a bit in order to get it to match a new situation than to re-engineer things to get it to work. But this is quite often a mistake. The problem with duplication is that when you have these different instances of code, if one of them needs to be fixed, it's probably for the same reason that other parts of it need to be fixed. And so if you then need to propagate these fixes across all these different pieces of code, there's the chance that you may miss some of them, and that will allow defects to propagate. Or there's a chance that there's a chance that you might make a mistake in making those changes to all of these different copies, because they're not quite identical. In many cases they will be very similar, but potentially not exactly the same. They might be different considerations required for certain other pieces of code, and with this it's very dangerous just to have these different copies of that code lying around. So duplication is viewed as being a sort of original sin in software design. It's something that can affect a lot of things throughout your program later on. Then, the Frank Lloyd Wright quote, the two most important tools an architect has are the eraser in the drawing room and the sledgehammer on the construction site. And the same thing applies to software development. If you get rid of code, or eliminate duplication, as it is also called, you're getting rid of code where bugs may occur, you're getting rid of code that you need to maintain, all sorts of things. You're making the code leaner, meaner, and just generally much higher quality by removing duplication. So what you want to do is refactor mercilessly. So we've already looked at refactoring from the test-driven development lens, and that fits into the red-green refactor model. The idea there, once again, being that you create a new unit, you start with a working program, you create new unit tests that fail, and then you change the code in order to pass the tests, and then in order to clean the code up to make your program more maintainable and more readable and so forth, you refactor it. And a lot of stuff comes under this sort of duplication umbrella. Duplication is not just when you have, one piece of code and then you copy paste it somewhere else. Duplication is also things like when information, for example, or data is duplicated. If you have data in one area and you, say, re-obtain it or redefine it somewhere else, that is viewed as being duplication, because you should come up with some way of actually reusing the original data. So that's why it's better to have, let's say you're writing code that needs to deal with a fixed number of entries, it's better to have some kind of constant value, or a private static final int storing that value, rather than to have references to a raw number like 5 throughout your application. Because when you go to fix that later on, a lot of the same kind of bugs that you can have with code duplication appear. You may, if you need to change that to 10, you may miss some of them, so you may not hit every 5 that you need to change, or in some cases you might have, say, a 4 somewhere, because you need to work out, we need to see if this list contains 4 or fewer elements before we add a new one. We might have a 4 somewhere, and we need to know to change that to 9. Or even worse, what can happen is that we may change something that we shouldn't have changed. We might have another 5 in our application, but one that doesn't refer to the maximum number of elements of this list. And so that can be very dangerous. If we have that isolated within some kind of constant expression, we can then just change one instance of the number 5, and then everything will be updated, and we'll know that we only update the right things. That 4, of course, is also duplicate information. We won't want to actually create a new constant expression that evaluates to 4 for that. We'll want to calculate it based on that number 5. So we want to use that constant expression, and then subtract 1 from it in the cases where we need 4. So this is the kind of thing that that is being talked about when we talk about eliminating duplication in test-driven development. So what is refactoring? The basic idea is that it's the process of improving or cleaning up code while preserving behavior. So refactoring doesn't make your code run differently. It doesn't make your code do different things. It may potentially make it faster, or could even make it slower. But it doesn't actually change the behavior of the code. The idea is that you use refactoring when you have working code and you want to keep that code working, but you also want to improve it. You want your code to be more modular, more reusable, more maintainable, more readable, that sort of thing. And individual refactorings are small transformations that preserve behavior to the outside. So this is behavior in terms of specification. If we say, for example, that a particular method sorts a given list, we're not caring how that list is sorted. So a valid refactoring could be to take a method that uses insertion sort on a list and make that use a merge sort instead, so that it works better for larger data sets. That would be considered a refactoring because it preserves the behavior. The method still returns a sorted list, but it changes the way in which it does it. And the other crucial part of this is that individual refactorings are small transformations. You're not changing a lot when you do a refactoring, and that's an important part of the process as well, because the more code you change, the more likely you are to end up breaking some of the existing behavior. So these individual refactorings, each transformation does very little, but together they do a lot. The idea is that they slowly evolve your code towards a better state. And this means refactoring, because they're smaller, they're less likely to cause serious system bugs, less likely for things to go wrong because you're not doing very much with each one, and that you verify that your system keeps working after each transformation. And so this is where unit tests come in, and regression tests. If we have this good unit testing suite, we can actually routinely check that our code is still working well. So, how do refactoring and design patterns link? Well, they're different things, but they're also sort of similar. The idea is that refactorings are a set of common transformations. So, when we refactor something, that's sort of a generic term used to mean that we've taken code and we've changed the structure of the code, changed how it works, changed what classes and methods are used, and so forth, while preserving the behavior of it. So that's the general approach for refactoring. But when we refer to an individual refactoring, we're talking about certain consistent approaches that have also been developed by the software engineering community. And they're part of capturing the conventional wisdom. The idea is that we've built up these common steps that need to be taken to translate code into better code. And if we apply these steps and we apply them in the way that they're supposed to be applied, we've minimized the likelihood of things going wrong, and we've also made clear what things are considered in need of refactoring and so forth. Design patterns are far more abstract though. They're based on the actual design. They're based on how classes fit together, whereas refactoring is, well, it's direct modifications to code. It is about the actual text you're writing to create an application. And it frequently works through creative destruction. So the eraser and the sledgehammer again. Refactoring will often remove code, especially when it takes care of duplication. So in that we will take, for example, a bunch of methods that do very similar things, and we will refactor them into code that we may refactor them into, say, one shared method that does different things based on a parameter, or maybe we take the common functionality between those different methods and we isolate it out into a method and have them all call it, or something like that. But sometimes the two overlap, and duplicate observed data being one example of that. So refactoring is dynamic, but the structures are known. So there are common refactoring structures. These are common processes or approaches to refactoring. They're transformations we make to our code, and we know about them because they work. And it's really about morphing bad code towards these proven structures, things that we know make for readable, maintainable code. Like with design patterns, there's a menu of refactorings. One popular source is Martin Fowler's refactoring.com, and it has a whole heap of different potential refactorings. I think I have that open in a web browser. And we see things like add parameter, change signature, remove parameter, rename function, change reference to value, collapse hierarchy, decompose conditional, extract class, extract function. These are instances of refactoring, and they tend to be very small changes, but they're viewed as being changes that improve code. And if we go over our code and we apply these refactorings when they apply, we will be gradually transforming our code into better code. Some are really trivial. Add parameter method, rename method are examples of that. Others encapsulate good software engineering practice. So extract method and collapse hierarchy are examples of that. They're not necessarily they're sometimes more detailed, but all about cleaning up the code. And now we have a whole bunch of different examples, and I will go over these, but I just want to draw your attention to the refactor menu, some of which we already have used. So I tend to use rename a lot. and these are called refactorings because they are designed to be transformations applied to code that do not change the behavior of the code. So when we rename something, we're trying to do a rename that will not actually change the code. So if we're not happy with a particular variable name, we can refactor it and rename it to something else. We'll just rename all occurrences. So note that occasionally we may have parameters that are actually also referred to in strings, and IntelliJ is able to go and fix that up in the case where we have that. Just make that a bit bigger. So this one is available from the refactoring method, but also available by Shift F6, and we can then go and type a new. IntelliJ even goes and suggests some names for it, but how good it does that can depend, but that's the basic idea. And the idea behind these refactorings is that they are safe. This is safer than doing, say, a plain text replacement, because you're at risk of potentially changing something else if you just do a straightforward search and replace. The refactorings know about the structure of Java code, and so they are able to actually change it. Now, not all of the refactorings on Martin Fowler's site are present in here. In fact, only a tiny portion of them are. And some of them are, depend on IntelliJ actually being able to make certain changes. Other things require you to actually go and do things manually in order to perform that refactoring. So the refactoring here isn't the same as the things that are on Martin Fowler's refactoring.com, but they do help you carry those out. So it's easiest to rename something by using the refactor rename and so forth. And it's often easy to, let's say, because we've got this text here, we can refactor that and introduce a constant, for example, and that will give us a constant name, maybe button text, whatever. And now, especially if we've used this in multiple places, now we can just all refer to this individual, might make this private, this individual constant value, rather than needing to re-specify this particular text. And that's often a good thing for especially numbers. There's a sort of adage in software engineering that the only numbers that should appear in your application raw are 0 and 1, and sometimes -1, and that anything else, if you're using other numbers, they should really be extracted out and given some kind of meaningful name. So probably not something like -1, but there's not really a more meaningful name because I only created it to demonstrate a point. But if you have this value actually referring to something, if it refers to some particular thing, then you want to have it being in a constant and then always referred to here, so that if you need to change that later on, you can just go and change it in the code. So, onto some of these specific refactorings. So, decompose conditional is a popular one, and the idea is to basically take a complicated if-then-else statement and extract methods from it in order to make it more readable and more maintainable. So in this case, we have some code where, we've got some nice constants here, so it's not all bad. We're just checking if the date is, before the summer start or after the end of summer. So the idea is that we have a winter rate and a winter service charge that's applied outside summer. Otherwise, we charge the summer rate. So how do we refactor that? Well, the idea behind decompose conditional is that we actually change this conditional here. We extract the logic here to determine, whether it's summer or not, and we put that in a method. And So in this case, what we've done here, we've also taken these and turned them into methods as well. So those are examples of doing an extract method, but they're related. And what we see here with this code is that, I mean, it looks a lot cleaner, but it's also a lot easier to read. We can look at it instantly and see exactly what it's doing. We may not know the exact logic of this not summer method, so we may have to actually dive into it if something's not working right or if we're getting unexpected results. But with this, you see, this code doesn't even need comments right now. This particular piece of code, it is self-documenting because we have these great named methods that are actually being used. It pretty much just reads, you just read the code and it's very natural. So this would isolate all of that logic in here, put that into one method so that we can incorporate that into our unit tests, for example, things like that. So this just makes your code a lot cleaner when you decompose conditionals. Another popular one is to take code that essentially forms a group and to turn it into a method. So the example here is that rather than just having all of these various things done in this print-owing method, we might just break that up into, say, print banner and then print details. And so we've broken that up into two methods here. But once again, they're pretty much self-documenting. We don't need to have this comment saying that we're about to print the details because we're actually calling a method called print details. We know exactly what that does. And any parameters that we need to pass to it, we can then pass to that easy enough. And this is something that IntelliJ can also help us do. I'm not sure how successful it would be, but let's just go and try to extract method here. And we'll call this, I don't really have a good name for this, but I'll call add button set visible. You can tell if the natural name for a method is very complex or describes multiple things happening, that it probably should be more than one method, but this is just a demonstration. So what it's done there is that it's gone and created this new method here, and it's worked out what parameters need to be passed in, and it's automatically created those parameters and moved our code into that method. And so by repeatedly applying that, we can end up refactoring our code to make it more readable. We can essentially remove comments because our code is now self-documenting. Not that it's a bad idea to have comments. In fact, it's probably in most cases better to have a comment than to not have it. But in this case, where the only comment just said print details, there's absolutely no need to have it here because we're calling a method that says the same thing. So this just makes our code look a lot nicer. It gives us more methods that we can individually unit test, and if there's some kind of regression happening later on, we're more likely to get right to the problem a lot faster. Encapsulate collection. So the idea here is that rather than, so in a particular case, we might have a student class, and each student has a set of the units that they're taking in a particular semester. And so we might just have get units and set units to enable access to that particular set. The refactoring to do here is to basically grant access to the results in a bit of a different way. So rather than providing access to the exact set, we provide read-only access to that set. So you might have some unmodifiable set here, something like that. We might create a specific type for it, or we might just return, an array, something like that, something that doesn't actually give other code the ability to go and change our set later on. And we've isolated access to it via add unit and remove unit. So if other code wants to go and change the students' current units, they need to make use of these two methods. They can't just get the units and then modify them or create a new set of units and then set them. And there's a bunch of benefits to doing that. One of the benefits is that, at the moment this is a set, and that's probably a pretty reasonable type to use, but we're locked into that set if we have public methods called get units and set units that take a set. Technically, we could potentially use something underlying, but the fact that this returns a modifiable set is a worry, because other code could take that set and hold on to it and, add units to it at any time. We would have no control from within student and no knowledge if something happens to that set. Instead, if all of the modifications have to happen through these two methods here, and if this just returns, an unmodifiable set that's a snapshot of the current state of the units that student is currently taking, then other code can't go and work behind our back, and we're not held hostage to this particular type. We could use an array list later on if we want. We could use anything. So this is a matter of making our specification here more flexible, in essence. It allows us more flexibility when we're creating the implementation and more flexibility to change it later on. Replace error code with exception. This is fairly straightforward, but this is another way of applying more flexibility. So rather than returning some kind of, we typically call it a sentinel value or something like that, some kind of explicit value that says this particular method didn't do whatever, wasn't able to do this thing, we can make that return an exception as well. That's considered a refactoring, even though that is very much a behavioral change, because it's usually a better behavior to throw an exception rather than returning some specific value. Because if you have a specific value, then all of the code that uses that needs to know about that specific value. Otherwise, it might just go and assume, oh, this account has -$1 in it. Okay. And, if the code doesn't handle that in every single case, then you will have unmaintainable code. Split loop. So this is an example of a refactoring that could potentially reduce the performance of the code, but most of the time it doesn't matter, and the benefits that it gains to readability are often more than worth it. If there's a real performance difference between this and the refactored version, most of the time the compiler will be able to spot that and do something about it anyway. But here we've got this code that, well, it does two things essentially, which is already a warning sign. A method that does two things should probably be two methods. But we've got it looping over this collection. I guess it's an array of people, and it's adding to this average age value, and then it's adding their salaries to this total salary value. Then dividing average age by the length of the people array, and then printing out average age and the total salary of all of the people in that array. How do we refactor this? Well, what we do is that we first split it up. Now, this is also an example of how refactorings work with each other. We often don't just apply one layer of refactorings. We will go through code that we've refactored and refactor it again, because sometimes refactorings lead to new refactorings. So in this case, we've duplicated the code, so we've actually done a duplication here temporarily. So in this case, we duplicate this loop, and we just work out the average age separately, and work out the total salary separately, then we print them out. And what that means is that this is now two completely separate pieces of code. We can then take that code and isolate that out and extract a method from it, and do the same with this. Before we split the loop, we weren't able to extract the individual components from it, because there's not a lot of point in extracting the individual line here. There's no point in having a add total salary method. Instead, we want to extract the loop, but we can't because that loop is doing two things. So if we split the loop, then we can just extract the individual portions that make it up and create much cleaner code that isn't doing two things when we do that. Okay, something we've already looked at a little bit. IntelliJ provides refactoring support through the refactor method. And of course, if something happens and you don't like it, you can always undo. IntelliJ is quite good about letting you undo changes you make through refactoring, because the idea with refactoring is to make these changes that don't actually affect the behavior of your program, just improve it. And so that's all available via this refactoring method, which might have changed a little bit since I took that screenshot. I feel like I didn't have quite as many things as that. Mine's a bit smaller now, but I think some of these have been moved into their own little submenus. But that's the basic idea. So, in summary, what we do, the idea behind refactoring is that we refactor to improve code quality. That simplifies its structure and increases its elegance. And that means that the code is easier to read, it's easier to maintain, it's easier to reason about. So one of the ideas behind these refactorings is that they make the code clearer, so that when we go to find where bugs happen, the bugs sort of more stand out a lot more. It's easier to find a bug that's in an individual method by itself than to find one that's sort of buried in a method among all this other processing. It's also easier to test that method and so on. And so refactoring is about making code that is more amenable to these kinds of bug fixing. It can be very difficult, not necessarily impossible, without automated unit tests, depending on the level of the refactoring you do. So the simple refactorings like extract method and rename and things like that can probably be done pretty safely without the need of any kind of unit tests. We're using IDE support for one thing to help us do that very carefully, and for another thing, we're also when the changes made are so simple that they're kind of hard to mess up. On the other hand, some of the refactorings are actually a bit more extensive, and the more things we do, the more the likelihood is that we will break something. So with automated unit tests, especially regression tests, we're able to verify, if you run your test suite before your refactor and everything's good, and then you after your refactor and suddenly you have failing unit tests, well, you know exactly what you did in order to cause those unit tests to fail. There's not a mystery there. And so it's a lot easier to go and make these changes very confidently in order to improve the code without being worried that the code will break. Because a lot of the time, the fact that a piece of code has been neglected for a long time is because that code is probably very important to something, but because it's so important and because it's potentially very arcane and hard to read, it hasn't been refactored all that well, or maybe ever, and people aren't able to maintain it, and so people just kind of avoid that particular piece of code. With refactoring, we're able to apply these very small steps in order to make the code slowly better, and we're able to, with the assistance of unit tests, we're able to go and fix things when they break. So we preserve the behavior specified by the API, because the unit tests verify that our code continues to do what the API says. And we change the way that behavior is realized, either purely through these code transformations that don't really change how the code is executed, or potentially through things that do improve performance, like replacing one particular algorithm with another algorithm that does the same thing. We refactored to restructure the code towards the best solutions known for each problem. Okay, so in summary, Software patterns are proven general purpose solutions. They're not code, but they can help you design better code. There's no need to reinvent the wheel when you use these. And we've looked at 3 examples of software patterns: factory method, singleton, and observer. Refactoring is something when you apply these small changes to code in order to improve its quality while maintaining its functionality. And it fits in very well with unit testing, test-driven development, and agile development more broadly, because agile prefers working code above everything else, and so refactoring, which improves code without stopping it from working, is therefore a very powerful tool. So, if you can get a copy of the Gang of Four book, it's a very good guide to these software patterns. If not, it doesn't really matter all that much, because all of this stuff is available. There's also plenty of online resources. Martin Fowler's refactoring.com, and there's a site here that's hopefully still up. Otherwise, just Google design patterns and you'll find a lot of good online resources that will give you more than enough information about what these patterns are, how they're used, and what situation which you will use them, and so forth. So take home, patterns and refactoring are both ways to improve your code. Patterns are for improving your high-level designs, how your classes slot in together, while refactoring is to make small code improvements. And thank you very much. A little bit shorter, but that's all I really want to get into for today. I'll see you on Wednesday when I do the second part of the assignment Q&A session, and that will basically be leaving off from where I started on Wednesday last week. So from where I finished on Wednesday last week. So we'll be continuing on through that, and we'll be able to look at things that people have expressed an interest in, which is session token handling and XML reading, and potentially some more into the network communication side of things. So hope to see you there for that. Thank you.